for this assignment, you would use this Excel data, right, for analysis. And the first question is actually a one sample t-test example, right? That you want to test whether average body mass index for the student population, right, where the sample is from, the average is greater than 24 or not. And you want to test that at 5% level of significance. So that's the alpha level, right? So when you do hypothesis testing, that's an important number there, right? So that's what you use to make decision. You would perform a test and get a p-value and compare p-value with this one, right? If the p-value is very small, that generally indicates that your evidence is so extreme when you compare with null hypothesis. So evidence is too far away from null hypothesis, right? Small, so small and small enough that it's less than 0.05, right? That indicate that your evidence is extreme enough for you to reject the null hypothesis. Right? So anytime you do hypothesis testing, you've got to have a null and alternative, okay? P-value is for you to determine whether you want to reject or not reject the null hypothesis. Right? Once you made that decision that you want to reject or not reject null hypothesis, then you can make statement about, conclude your analysis about alternative hypothesis. Oftentimes, our alternative hypothesis is the purpose of the research, right? So sometimes people call that research hypothesis. Okay, so this one we have the data download, okay, and it's not ready. We have height and weight. They're not BMI, okay. And if you scroll down, actually, there are some extreme values. Sometimes this happened, right? People just wasn't careful. Supposed to be 70-something, just typing the first digit and that's it, all right? So that apparently it's a mistake. So you would actually go back and look for this person and find the accurate data, or maybe if you don't have the clue, you just have to remove it, right? You can remove it from here, or you remove it from R, either way, right? So I can remove it from here. Now, if we have large data, of course, the first thing you would do is what? In R or in any software, you draw pictures, right? Maybe box plot or something, then these numbers will show, right? So that's always the first thing you have to do. You don't want to just, I know my t-test. I got this data, I got this variable, I'm going to run the t-test right away. That's not the right thing, right? You got to first check in the integrity of the data, right? Everything is okay, then you run the analysis, right? I try to save time without going through those graphs. I think you can do those, all right? So I'm going to just save this. Where did I save that? So maybe save it in some place that I know. This PC, maybe. It's probably in the download folder. Okay, it's in the download folder. Okay, so I'm going to close that and then open the R commander. First R. Then click load package. Go to R commander. Now you know that we have R commander and R commander plugin IPSR, all right? Actually, there's a lot of R commander plugins. Some R commander, John Fox has a list of methods you can use. If you want to use more, or somebody actually modify his options, or add something new, something else, right? You can just, find their plugins and then run their plugin along with this, right? Or sometime, actually, I think, well, anyway, there's a long list. Let's not. So let me just use that, right? R commander. Okay. It took a while. Okay. So you know how to import that Excel file data, import data and from Excel files, and then we call this data set 1 and click OK. Variable name in the first row of the spreadsheet, just in case you have it. We have it, all right? If you have a data sheet that doesn't have first row, then you don't want to use that. Just check that off, right? So there are these options for you to use. And I just click OK. Look for that one. I think that's this one. Open. And look at the data. It's there, okay? And those, they're not available, so that's good, okay? you can make histogram for height and weight if in case, right? You haven't done any exploratory analysis to see whether there's outlying or error data in there or not. Okay. So what then? Well, next thing is try to produce that BMI variable. We don't have BMI, but we have weight and heights, right? And weight and heights were actually in what? Pounds and inches, right? So if it's in matrix, if it's in meters and what's a kilogram, right? Then you will use one formula. If you use inches and pounds, you have to multiply 703, I remember, right? So what you need to do is just compute that. You click data, manage variable in data set, and click compute new variable. Then you can compute this new variable. I'm going to call it BMI. And this BMI will be, you can have like 703 and multiply, that's the asterisk, and then weight and divide by, I believe it's height square, right? Height square, height square is double asterisk, and then 2, right? So if I click apply, OK option. Okay, and then look at the data. Then you have these BMI, right? You know about BMI, right? The regional range is like from 20 to 30, 40s, right? So this look right? If you see something that is extremely large or extremely small, that means you don't have the right numbers. So that's BMI. So our goal in this problem is for testing whether the BMI on average is greater than 24 or not in this particular sample population, right? So what should be your null hypothesis? That's average BMI of the sample population is 24, right? Or equal to 24. An alternative is average BMI is greater than 24, reflecting this research questions, right? So some students like to use the notation mu, which is great, right? But actually, if you don't know how to bring up that mu, that's actually a symbol, right? So you can click on symbol font and type M. M is the mu. M in Greek is mu, right? So you can do that. And then this is a t-test, right? So the sample size is not really so large. So usually we would like to test for normality to see whether the sample is likely from a normally distributed population, right? So this is for checking normality assumption. So what you would do, since you have a data checking normality, just click statistics, summary, test of normality, and just use a Shapiro. There's tons of them, right? Shapiro is a pretty popular one, right? So click that, click OK. Oh, I'm sorry, I didn't check the BMI. Right? Click OK. And you got the p-value of 0.2, which is higher than 0.05, right? In testing normality, the null hypothesis is that the distribution is no different from normal, okay? Or it's likely normal. But your p-value is very large, so don't reject that. That means you can accept the normality assumption. Is there a distribution that is exactly normal? Normal distribution is a mathematical model, right? Nothing in the world that is exactly, I shouldn't say nothing in the world. That's a too strong a statement. But most of the time, right, when you look at a distribution, they're not exactly normal, but their distribution shape just fit the normal pattern very well. So when you have data like this, right, and when you work on a t-test, the t-test will perform pretty good, right? Will have better power. Okay, so that's an important assumption you want to check. Now, if this assumption valid, means you have a p-value less than 0.05, right? They're a non-parametric test. But however, you probably heard that in my lecture. I said the t-test is somewhat robust against normality. That means what? If your distribution is not quite normal, right? This t-test still perform pretty well. So you get a p-value of 0.0, maybe 12 or something like that, right? Or 0.023. That's less than 0.05. Now your t-test probably still pretty powerful, right? So, but if you have 0.000 many zero, that means you have data so extremely skewed or something, right? And then you should try other methods. In our class, we've learned non-parametric tests, but there are other methods, right? There are bootstrapping methods. There are other alternative computing intensive methods. But anyway, so this one, we accept normality so we can actually draw a conclusion for this one, right? The normality assumption is acceptable. You can say that, right? Since p-value, what was that? 0.2 something, right? 0.22 is not less than 0.05. The normality assumption is acceptable. That's a good statement, right? Because the goal for this test is for testing normality, okay? And then you want to report the p-value for the t-test. Now this time you want to do the t-test. So to do t-test, click statistic, means, single sample t-test, okay? And you want to test BMI on average is greater than 24 or not, just use the test value, mu under null hypothesis 24. And you want to test whether that mean population mean is greater than that mu 0, that 24 or not, right? I'd rather they put a mu 0 here too, right? But anyway, that's good enough, right? So you just click OK. You get this p-value for t-test that is 0.07, which is not less than 0.05, okay? And it's actually for testing true mean is greater than 24 or not. Okay, so 0.07 p-value for p-value is actually 0.07, around 0.07, right? This p-value less 0.07 is not less than 0.05. So therefore, null hypothesis. Well, we do not reject null hypothesis. Null hypothesis. And that's not a good enough answer, all right? This is just a decision on whether you reject null hypothesis or not. The important thing is to properly conclude this test, right? You have a p-value, null hypothesis not rejected. That means there's no sufficient evidence to support the alternative that the average average BMI is statistically significant greater than 24, right? So there's no sufficient evidence to support the alternative hypothesis that the average BMI of the sample population is statistically significantly greater than 24. So that's a better statement, right? Okay. I just like students to have a habit, right, of writing it this way. Now, when you write a research paper, you don't have to write it this way, right? But if you have a good habit in writing this way, anytime you're writing a conclusion, you realize that, oh, okay, now I don't reject null hypothesis, my evidence is statistically not significant enough. All right, this is a statistical test, right? So often these statistical tests are used in a sample of smaller scale, right? And the evidence shown with the sample size you have, right, going through this test, your evidence show that the difference is not statistically significant, right? Or the average is not statistically significant greater than 24. Okay, so hope you know that, right? I think I mentioned in class what is statistical significance and practical significance, right? So it would make sense. Now, anytime you're doing these tests, you will have a sample mean. Now, your sample mean when doing this problem, you could have a sample mean that is maybe 26 or 28, okay? And you're doing the test, you find out that just because of the sample size you select that you choose for doing this test, you may not find the outcome is statistically significant. That's possible too. It's all sample size. Right? But however, you also know that people talking about large, big data nowadays, right? When you're dealing with big data, that's a different thing, right? When you have data that's really huge, anytime you do, if you like to do hypothesis testing like this, oftentimes you will see significant difference, right? So while you have that kind of situation, you're going to consider different type of way to analyze your data, right? Usually large sample, you're going to have great power in detecting difference, so you're going to always have that. But anyway, so that would be a proper way to conclude your t-test, right? Not seeing any difference. Now, part B is find a sample size so that we can have 90%, 95% power to detect BMI average, that is, have a standard deviation from the mean. Okay, so that's a sample size issue related to testing hypothesis. Okay, now you have maybe I can quickly take you to the formula. Okay. Oh, clicking the wrong one, but if you remember the formula for this, right? That's the last part of this. Okay. When you have one-sided test, right? You have a formula like this or this. It really depends on whether standard deviation is available or not, right? If standard deviation is available, then you can specify the effect that you wish to detect, right? Just by its units, 10 units or 2 units. But if you don't have standard deviation, sometimes people specify the effect size or the size you want to detect, the difference you want to detect in terms of number of standard deviation. That way, you don't need to have standard deviation because sometimes you're probably performing certain kind of study you've never done before, so you don't have data, right, to estimate standard deviation. Okay, so for this particular problem, it's this case, right? We're talking about half a standard deviation. Okay, so half a standard deviation, that means what? This delta, this will be 1/2. You don't need standard deviation. If this part is half a standard deviation, so that's 1/2 standard deviation. With this standard deviation cancel. If you still remember your algebra, right? So it's just essentially the same thing. Same formula, just use it in a different way. So we need 95% power. Now power related to this beta, right? 1 minus beta is power. So beta, if it's 95%, beta is 0.05. So you should use a standard normal table. Or R, commander, right? Use a standard normal distribution to calculate the 0.05. That is around 1.645. If you do a lot of problem like that, you have that memorized, okay? And then the test at 5% level. So again, Z alpha is 5%. If it's one-sided test, actually we were doing one-sided test, testing whether the mean is greater than 24 or not, right? So that's one-sided test. So you have a Z of alpha over 2, alpha and a Z of beta, and both alpha and beta are 0.05. So both of them are 1.645, right? So this one shouldn't be too bad. 1.645 plus 1.645 divided by 1/2 raised to the second power. You get the answer. So the sample size should be 1.645 plus 1.645, and then this thing divide by 1/2, let's say 0.5, right? And this whole thing, you square this number. Oops. You square this number. That would be the answer, right? So if you have Excel, and of course, while you're doing the exam, you can use Excel, right? So you can use Excel in so many different ways. If you're smart enough, right? You can make the work so efficient for yourself. Anyway, so for this one, I can just copy this, paste it into Excel. Okay, I'm going to make it a little bit larger. Okay, remember when you use Excel to do some calculation, you want to start with equal sign. So type in equal sign, right, and then parentheses to actually calculate the sum of 1.605 first, and divide by 1/2, and raise to the second power. Of course, Excel doesn't take that, right? So you're going to do like a shift and 6 and 2. That would do the square. Okay, and then hit enter. So that's 43.29. Okay. So here is like equal to 43.29. Oh, pardon me. Okay. So the sample size should be actually, usually we rather use a lowercase n to denote the sample size, right? So you will always run up to 44. Always run up, right? When it comes to sample size, always run up. To be more conservative, the larger the sample, the better the power, right? Okay. Any questions? So that's the answer to this. Okay. And part C, we want to find 95% confidence interval estimate for average BMI. So we have that BMI data. So what we do, just run through this again. It's not this one.
Hey, Dr. Chang.
Yes.
How did you know that it was just a one-sided test? For that?
You read the questions here, right? This actually, the whole set is related, right? This whole question is about actually testing hypothesis that actually mean is greater than 24 or not, right? I think if you give me a two-sided test, I will give you the answer to it, right, for this one, because you think that I didn't mention it in here, right, in this question. So I would still give you credit, so don't worry if you do a two-sided, okay? But does it make sense? Knowing that it's one-sided because I say I want to test whether it's greater than 24, right? So that's one-sided. Okay? So and inside this statement, you can see also it's one-sided because you're testing true mean is greater than 24, right? This is one-sided test output. And this is a one-sided confidence interval, right? Sometimes people do that, right? Oftentimes people do two-sided confidence interval. But anyway, so if you want to do this, you want to rerun this again, choose the two-sided. If you check alternative, that's two-sided test, and your confidence interval estimate will be two-sided. Okay. So just click OK. You get the confidence interval estimate, right? The mean is 25.179, but the interval is this, right? So interval, remember the interval notation, smaller value on the left, larger number on the right. So if you want to report that interval, right, this is the proper way to do it, right? Don't put 26 in front and then 23 next. That would be a wrong way to express this, right? Or you can use the midpoint. That was this is actually 21, 25. 25.17952 and plus or minus, I think you can do a symbol, plus or minus, right? And then what's your margin of error? This confidence interval is calculated using this point plus margin of error to get the right end. This number minus margin of error to get the left end, right? So you can find the difference of these two numbers and then divide by 2. That's margin error. Or difference between this one and this one, okay? Or left end point and that one. That will give you the margin error, just in case you wish to report the outcome using the point estimate and the margin error, right? So if you want to do that, then you probably calculate it very quickly. That's equal to the difference of the two, right? Oops. So about 1.62 something, right? So copy, paste it here, paste the, okay. So there are these two ways to report your confidence interval, okay? Part D, find sample size that will require if you wish to estimate the mean with a margin of error no more than 0.2, right? So this is a sample size question related to estimation, right? Remember in statistical inference, there are two things we do. One is hypothesis testing, one is estimation, right? So this is a sample size calculation when it comes to testing hypothesis. This is sample size calculation when it comes to estimation. Students often confuse, right? Stop Okay, so be careful on these. So for that, you have learned a formula for sample size. Let's say this is for hypothesis testing. So, it's confidence interval. We have interval estimation for mean, and then we have sample size calculation. Here, right, the formula. Sample size for estimating mean. Right, so that's the formula. We use a z-score instead of t-score. You can use t-score. It's just complicated, right? So I just like you to practice at least once, right, using a z-score to get an idea. Getting a sample size is achievable, right? So when you have a confidence level, you know this is z alpha over 2, right? If it's 95%, this is 0.025, which is 1.96, right? Standard deviation, you will estimate it with maybe if you have any prior study, and then E is the margin of error, right? So when you come to this question, come to this question, we've been doing 95%, right? So if it is not asked or not telling, right, what level, it is 95%, right? So your sample size will be your 1.96, which is z of alpha over 2 in this case, right? And square, or maybe I can do them all. Then this multiply. Standard deviation, use the data to estimate the standard deviation, right? So we have the data, and this data had standard deviation. I wonder if we got them or not. If we don't, we can just quickly get it. Summary statistic, right? Numeric summary, the mean of BMI, we get a standard deviation of 4.665, right? So maybe we can just use that. So it is actually, let me just do it here, 1.96 time, what was it? Bad memory. So that was, I had it, right? I copied it, and I forgot I copied it, so I'm going to just paste it. Yeah, okay. And then divide by margin error, we said it's no more than 0.2, so that's a margin error, 0.2, right? So we then put parentheses on both sides.
Dr. Chang?
Yes?
Can you explain why you used 1.96?
Okay. Because this is about 95% confidence interval, right? 95% confidence interval. The confidence interval in my lecture is 1 minus alpha, okay? And in the formula for this, is z of alpha over 2. Z of alpha is 0.05, z of alpha over 2 is 0.025. So that's a z-score that is right tail is 0.025. So it's like 0.975 quantile or 97.5 percentile from a standard normal distribution. Okay, so that's how we find that. You can either use a standard normal table to find that, or t-table. Believe it or not, t-table can help you to find this. Usually the bottom row of t-table is for t-distribution with degrees of freedom infinity. T-distribution converges to standard normal, right? So those t-score can also be used, right? Or
so Dr. Chang, why would you use that instead of 1.645?
1.645 is a z-score that is right tail is 0.05. We need, look at this formula here. So I said that the confidence level is 1 minus alpha, right? So if confidence level is 95%, alpha is 5%, 0.05. And when you calculate this thing here, you need a z of alpha over 2, which is z of 0.025. So you're looking for a z-score such as cumulative distribution is 0.975, and right tail is 0.025. Okay. Hope that makes sense. Now, you can use Excel, right? The function, special function to calculate these t-score and the z-score too. If you use normal.dist, this is calculate normal probability. If you use normal invert, right, this is for calculating those z-score. Okay, so if I do this, And they ask you to specify the probability. You say 0.975. That's cumulative, left tail cumulative. Right tail 0.025, left tail is 0.975. And the mean is 0, standard deviation 1. If you do this, you get 1.9, something like 6, all right? Use this one. This is so-called a z of 0.025. A z-score such as right tail is 0.025, or the 97.5 percentile of the standard normal distribution. Okay. I hope this makes sense, a way to do it. Okay. There are many ways to do this. Actually, unfortunately, I didn't have that. Well, maybe we
Dr.
just
Chang,
Yes?
the number that you just computed in Excel, that's the z-score then?
That's a z of point. This is hold on. This is a z-score. This is a z of 0.025.
Okay. Did you
Okay.
have to install the stats package on Excel to use those?
No. This is a regular Excel function. You don't need to install
Okay.
this package. Right?
Okay.
Yeah.
Thank you.
Yeah. This is one way to do it. All right. Or you can just look up a standard normal table. Let me just find any standard normal table. Standard normal. Maybe this one. There are all kinds of tables out there, right? And I hope you can use any table. So this is z of to me to 0.975, right? Z score or 0.975 quantile of a standard normal distribution. That's 1.96. That's how you get it, right? You should be able to do this now, right? But anyway, there are other places you can find this. You can use the R Commander, right? R Commander can give you this. If you go to R Commander, click distribution, that's a normal distribution, right? You can find a normal quantile. That is a normal quantile, okay? So you click on normal quantile. The probability is Q. It gives you left tail, right tail. If you want a left tail, a z-score with the left tail is a certain proportion, like 0.025, right? Standard normal is mean 0 and standard deviation 1. So this normal distribution is read for those z, right, standard normal. So you have a left tail, this is lower tail, check it to upper tail, that's right tail. If you want to find a normal quantile, standard normal quantile, which is those z-score, right? That is right tail, it's 0.025, click OK, you get that. The same thing. This is probably easier. I don't know, whichever you prefer, okay? You can use the R commander to do it. Continuous, normal, right? Check the normal quantile for those special z-score, right? So maybe we probably will practice a few more times. We'll keep using this, maybe, right? Or if you want to explore Excel, right? Either way. Okay, but anyway, so for this one, we haven't finished it. So we need let me double click it, right? 1.96 because this is 95%. Actually, you just memorize it. Right? I often recommend students to memorize two levels, 95% and 90%, right? And or z of 0.05 and z of 0.025. Z of 0.025 is 1.96. Z of 0.05 is 1.645. You have that memorized, right? Or, write it down somewhere, right? So you don't have to redo all these because it's just, in our class, right, this will happen most of the time. I would just give you the standard level, right? Okay? So you have that z-score, z alpha over 2, yeah. And then the standard deviation, okay. Then the margin of error. So the z-score times standard deviation divided by margin of error, and this whole thing takes square, right? And you get this sample size, 29. So let me copy this thing here too, right? So that I don't have to type it again. Maybe I will just make this exponent. Okay. And this should be, what was it? 2090. Actually, I had it. No, 20. I didn't copy it right. Okay. So 2090 point something, and you always round up to next higher integer 2091. That will be your sample size. Okay, and that's for estimation. Okay. This will give you a sense. Sometimes you may be a manager or something. You want some people to go out and do an estimation of the mean. You don't want to give them an unrealistic, margin of error, because for this case you would need to 2,000 cases, right? Are you able to get 2,000 cases, right? You'll be asking for trouble in this situation. Okay, so be able to calculate sample size is quite important. Right? Okay, so that's that sample size required for estimation, right? And part E is actually for estimating percentage of students who exercise regularly in the past year. Okay, so this is estimating proportion. Estimating proportion is different from estimating mean. Okay, so estimating proportion, we actually learn a confidence interval estimate formula. Usually it's the last part. This is the formula for estimating proportion. You use a sample proportion, right, and you use this large sample formula with a z-score there, right, and that's a formula for estimating proportion. So this one, you want to do a 95% confidence interval estimate for percent of people who exercise regularly in the past year. Do this problem by
Andy?
hand. Yes?
Got a question.
Yes.
Thank you. Dr. Cheng,
Oh, okay.
would you round up to, I'm sorry, just to go back to the last one, would you round up to 2091?
Yeah,
If,
that's right.
If there was anything after the point, I assumed you wouldn't round up to 91 if it
You
were
always
less.
round up. You always round up. Okay.
Even
When
if
it comes
it's.
to, yeah, that's right. You don't do regular rounding, right? It always round up to next higher integer. To be more conservative, you really want your interval to be large enough so that you have that level of confidence. Okay.
So
that's
anything
the
after
habit.
the decimal.
Yeah. Even you have a 0.1, I will round up to the next higher integer.
Okay, thank you.
Okay. Yeah, always do that, right? When it comes to sample size estimation, we always do that. Now, does it matter if you round down? I don't think it'll really matter. Okay. It's just in principle, all right? We always like to round up. Okay? Good question. Thanks. All right. Okay. So now let's get back. So this one we want to do a 95% confidence interval estimate using that formula we learned. All right. So actually that's this formula, right? P hat plus or minus z-score times square root P hat 1 minus P hat over n. Okay. So you have the data, in fact, let me see. We have the data here, exercise regularly or not. That's this one, right? Have you been doing exercise regularly? Yes and no. So you can use Archimedes to help you to quickly get some statistic. Have you exercised regularly? All right, this one, click OK. And you get the frequency, right? Actually give you the proportion, 59.46. That's even better, right? So you have the p hat already, right? The p hat is, you can say p hat if you want, right? Or whatever, let me see, what is it? 59.46. So that's your p hat, right? If you have equation editor, I don't have it activated, but you can really do a hat on top of it, okay? So the interval estimation will be this p hat plus 1 minus, let's just do this inside Excel first, right? So we have a p hat that is 59.46, right? And the confidence interval estimate will be this plus or minus marginal error. So maybe let's find the marginal error. Marginal error is what? That z-score, z alpha over 2, what would that be now? If it's 95%, 1.96, yes, right? 1.96, right? And then plus or minus, multiply, right? Multiply square root, then this proportion time 1 minus this proportion divided by sample size. I forgot to check the sample size. What was the sample size there? 37, all right? 15 and 22, 37. So that'll be 37, close parenthesis. So that's, oh, what happened? What did I do? 1.96 times square root of A1 times 1 minus A1. How come? Let me see.
Dr. Chen, why did you not change 59.46 to a decimal?
Ah, yeah, that's right.
Oh, okay. I wanted to make
That's
sure
right,
that I
that's
did it.
That's right. Thank you. Thanks for reminding. Okay, that's the reason, right? Thanks a lot, right? Okay. So you get, what is this? This is margin of error, right? This thing is margin of error. So what you do is just use this, subtract from here, this subtract this, right? This minus this plus this to get the two endpoints, right? Or you can answer the question like 59.46%, and then like what I did, simple plus or minus. Margin of error was 15.82, right? 15.82%. So that's your confidence interval. Okay. Make sense? Right? Or if you use this, subtract this plus that. Let me try that, right? So you can use this number, subtract this number to get the left endpoint, and this number plus margin of error to get the right endpoint. Okay. So 43.72. Right? Oh, let me just type it here. Right? 43.64% to 75.28% if you want. So that's another way that you can answer this question. Okay. Any questions? All right, that's easy. Okay. If you plan to conduct the same study again to estimate percentage of students who exercise regularly, we should have a margin of 2%. How large a sample will be needed? So that's, again, the sample size issue, right? There are two formulas for it, if you recall. If you never done such a study, then you will use this formula in the bottom, right? If you had some study, you have some prior knowledge about proportion, and you think that's pretty close, then you can use this formula, right? So if you assume that I had know this proportion, right, then I can use this formula. So it'll be sample size will be 95%, right? Z alpha over 2 is 1.96 or 1.96 and square. Divided by the margin of error, what did we say, 2%, right? We want it to be 2%, so numerator is 0.02 and square, right? You want to multiply the estimated proportion, that is this one, time 1 minus this estimated proportion, okay? So what I'm doing is using this formula here, okay? The z-score that you need in that confidence interval estimation formula, that's z alpha over 2. 95% is 1.96 square, divided by margin of error, 0.02, 2% square, time the proportion, time 1 minus proportion, right? So that's how I got this. So you get the, well, that's still a very large number, 2315. Okay, so copy, put that in my, oh, if I can right click and see if I can copy the formula. Oh, there's the formula. No? What did I do? Let me see. Oh, that was in here. Okay. Okay. So that's the, this would be 0.5946, and 1 minus 0.9546. So let me make it lowercase, and that would be the, well, not yet the answer, but round up 2316. All right, round up to next high. Look at this. This is 0.052. I still round up. Okay, round up to the next integer. But I tell you the truth, if you really do this and run down, I'll give you credit. Right? You know how to do it. So really not a big issue. Okay. Any questions? Okay. The part G is asking you to find confidence interval estimate using this method, right? But by R command, I mean, not R command, but by using R, right? So I introduced this HMISC, right, package. So you should have load that package. Just use a bin conf function, right, to do that, right? So what you do, just go to R console. Now, I just want to make sure that I have that loaded. So that's HMISC. Right? We already have that installed, and you should have that installed, right? You want to make sure that one is installed. Okay. Then just do the. Then.
Hey, Dr. Chang.
Yes.
Will the exam have this type of R commander? Will we have to load separate packages and load data into R commander and such?
Well, now for the exam, you done your web assigned problems, all right? The kind of question I would ask you will be what's your confidence interval? So whatever method you use, that is fine, right? I think for this particular problem, you don't really need that. If you like to use it, well, actually, if you know how to use it, right, you'll get your answer very quickly. Once you have the proportion, right, it'll be done so quickly, just a few clicks. I mean, type this function. Or you can just use Excel or do hand calculation, right? You don't really need it, right? If you have other tools, right? Okay? Am I making sense? I hope I answered your question. You don't really need to do that. But if you want to do this, make sure just, you have this package installed, this HMISC, right? I think you should have it, right? Because I think I've shown you one time in class, probably, right? This HMISC, right? HMISC, right? You click OK, load that function. If you don't have it, you just click Package, Install Package, right? And I have a video for it, I think, right? That for this thing here. You just look for mirror sites, and it'll show you the list of all the packages. You look for that HMISC somewhere here, and just code OK to install it, and then you'll be able to use it. Okay. So for the exam, whichever way that you like to do, it is fine. Okay, just make sure you know a way to do this problem. I introduced several ways for you to do this. All right. So hopefully, so this one, when you do this, of course you got to know what's your proportions, right? So you remember that in your R commander, you estimate this is 22 out of this 37. Okay, you want to estimate the proportion of yes, right? So 22 out of the 37, and I think it's what? I can never remember this thing. Methods, I think equal double quote asymptotic, right? Misspell. That's a problem when you try to do it fast, right? Okay. So that's the answer, okay? The lower bound and upper bound and the point estimate, Questions? So the answer to this will be still the same, right? Should be the same, exactly same as this one. Okay. And if you run it in R Commander, now R Commander has an option for that, right? If you run R Commander, where is it? R Commander statistic and estimating proportion, single sample proportion, and then this is yes, you have doing regular exercise or not. Normal approximation, so that's good. If you use a two-sided test, click OK. They will give you a confidence interval, right? But they will use a different way to do this. So, this result will be different from the outcome when you use the formula we learned in the course, right? This is using a different approach, using a so-called unbiased approximation approach, right? So a different way to derive this result, and you get a confidence interval like this, and it's different from what we had there. Right? This one actually, this one actually is not for estimating yes. This one is actually for estimating no, right? Yes and no. Yes actually is a letter Y in the alphabetic order. Y actually is below, later than N, right? So when it is doing the estimation, it'll estimate, if you didn't specify, it'll estimate the outcome in the lower rank, right? So you have 1 and 2, it'll estimate 1, right? So if that's the case, you want to reorder your data. I think there's a way to reorder factor level, right? Want to reorder exercise. No was 1, so it was estimating no, right? So you want to change them to yes is for that, right? And click OK. And if you rerun this again, then it'll be 59.45, okay? So be careful, right? But when we do the exam, you don't have to worry about using this to get the answer, because this is not going to give you the answer using the formula we learned in our class. So don't worry about this one, right? Just in case you're curious, why I'm not getting the right answer? This is confidence interval. Well, because of that, right? In the past, sometime I actually give you that formula. That formula looks so ugly, so complicated, right? You can, Wikipedia, right? You can find it, okay? Okay, any questions? Is everything okay in Cleveland? Yes, I hope. Okay, good. So, I forgot to put this result from R Commander, right? R Commander is this one, right? So that will be something like 43.49, okay. Okay, so that will be answer